Okay, and welcome back to the next video. Okay, so now we are looking at the K of molecule and the temperature. Yeah, so earlier on we were talking about how does a molecule move so that temperature increases or temperature decreases. Now I want you to see something quite amazing here, I think. Okay, the K of molecule, okay, is we know now is directly proportional to the temperature. So in other words, what you know formally as thermal energy, right? Okay, is nothing but your kinetic energy of the particles. Okay, uh, in fact, okay, of course, what I'm going to say next, yeah, please don't write it in an exam, okay? But thermal energy actually does not exist because effectively, thermal energy is just the kinetic energy of the particles, okay? If the particles are not moving, there's no thermal energy. If the particles are moving, there's thermal energy. Okay, so basically, thermal energy is just a short form for the kinetic energy of the particles inside the entire system. Okay, so we know that the faster the particle move, okay, the greater the thermal energy. Okay, so greater Ke, just a last summary, will lead you to greater temperature, and lower Ke will lead you to lower temperature. Okay, now please remember that this is half mv square directly proportionate to temperature. Okay, so if my velocity increases by 2 times, my temperature increases by 4 times. Okay, please remember your common test for term 3, question 1. Okay, the trick question that most of your, yeah, in fact I think only 2 of you all got it right. So yeah, really most of you all got it wrong. Okay, not because you do not understand hydraulics, okay, but because you're tricked by the r square. Okay, so in the same manner, okay, note that this is v square. Okay, so I'm gonna stop here now regarding uh, the relation between speed and temperature. Okay, now I'm gonna go back to the slide and look at this objective now. Explain. Okay, sorry. Yeah, explain the pressure of a gas. Okay, in terms of the motion of its molecule. Okay, so um, now if you were to consider something, right? Okay, so let's look at this box here. Okay, and there's a molecule here. Okay, and the molecule is going towards the wall. Okay, so you do remember that pressure is effectively force over area. Okay, and force is effectively mass times acceleration over area. So if the ball is moving at 7 meter per second, I mean the molecule is moving at 7 meter per second, it ends up here, and the velocity becomes 0 meter per second. Okay, and if let's say this took place over 1 second, sorry, okay, so this entire event took place in 1 second. Okay, acceleration is basically 7 minus 0 over 1, which is 7 meter per second square. Okay, so let's say for instance it is something like this. Okay, so basically we have the mass of the particle times the acceleration of the particle over the area. Okay, so this is the area that was hit. Okay, this over here, this green area. Okay, this area was being hit by the ball. Okay, so um now I want you all to see this relation. Okay, for acceleration, right? Okay, is acceleration greatest uh if object is moving faster or slower? Okay, so I want you all to consider this. Okay, so we have a 7 meter per second. Okay, it travels towards a certain place, and it ends up at 0 meter per second. Is this faster? Is this let's call this a1. Okay, uh, and let's say it's also 7 meter per second, but it's 3 meter per second now, and let's call this a2. Okay, both of these takes place in 1 second. Okay, which a will be greater? Is a1 greater than a2, or a2 greater than a1? Okay, of course, yeah, if you do your calculation, you should realize that a1 is definitely greater than a2. Okay, okay, now if we know that a1 is greater than a2, and we look at this equation again, okay, from 7 meter to 0 meter per second and 7 meter to 3 meter per second. Okay, of course, the same can be said for 3 meter per second to 0 meter per second. Okay, so it actually depends how fast the ball is moving at first and how slow it is moving at the end. Okay, so we look at the start, okay, and the end. Okay, we are interested in these two. Okay, so we realize that the greater the acceleration, okay, will lead to a greater p. Okay, so let me erase certain things here. Okay, I'm going to erase this part here. Okay, hold on, sorry, give me a minute. All right, okay, and we'll reconsider this. Okay, so faster object, okay, or rather you shouldn't say faster object. Okay, an object with high acceleration. Okay, please do note that you really need to understand the definition of acceleration here. Okay, if you do not understand, you have issues with your kinematics, please come look for me. Okay, so an object with high acceleration, okay, will definitely lead to high pressure. Okay, so what we have here, remember, is P equals to force over area. Okay, using Newton's second law is ma over area. Okay, so basically P equals to ma over area, and P is therefore directly proportionate to acceleration. Okay, so in other words, P increases, then A also increases. Okay, so this is the relation that I want us to see with regards to pressure and as well as uh, pressure with respect to speed. Okay, so this is respect pressure with respect to speed, or in fact acceleration. Okay, the next thing that I want to introduce to you all, which we will do in class, is this formula: PV equals to alpha T. This, we call this the ideal gas law. Okay, this is not the full ideal gas law yet. Okay, if you're going to take physics in your JC, this equation may change, but just by a bit. Okay, alpha is a constant. Okay, which at this point of time we are not interested in the value. Okay, now I want you all to see the formula. PV is equals to alpha T. Okay, and there are three conditions that I want us to take note. Okay, so I'm going to draw three brackets here. Okay, now the first condition is for V and T. Oh, sorry, is for when P is constant. Okay, the second condition here is when V is constant, and the last condition is when T is constant. Okay, so you do realize that when P is constant, then basically V is directly proportionate to T. And sorry about that. Okay, you do realize that when P is constant, V is directly proportionate to T, and therefore we have something like this, a linear graph. When V is constant, P is directly proportionate to T, and we have a linear graph as well. Okay, however, when T is constant, okay, then P equals to alpha T over V. Then you do realize that this is an inverse graph, and the inverse graph will look something like this. Okay, these are the three graphs that are most important in this chapter, and I need you all to understand. I will explain more in class during the question time. Okay, how this equation is formed, and what are the significance, okay, impacts, okay, what are the impacts of these three graphs. Okay, so yeah, we might do an experiment on Monday. Okay, and we'll see what are your prediction, and what do you think you observe, and so on and so forth. We'll do the POE again on Monday. All right, so that's it for kinetic model. Okay, I will upload one last video on the conclusion on kinetic models. I'll let you all know again. Okay, so that's all for today. Thank you so much. Okay, bye bye.